Welcome to Physics3364, Laboratory Electronics. I'm Dr. Bill Ashmanskas. You can call me Bill, or Dr. Bill, or Professor Bill, whatever is most comfortable for you. Dr. Ashmanskas seems like an awful lot of syllables, so most people seem to wind up saying Dr. Bill. Let's go through lab number 1 as a preview, mainly to demonstrate the lab technique that I would like you to try to emulate in class. You'll see me wire things up and use the lab instruments so that when you do it in class, you can try to use a similar technique. This will be especially important later in the semester as our circuits become more and more complicated. As the number of components you wire up grows, it will be much easier to debug if you follow a neat and organized pattern, and if you try to make your wiring look as much as possible like the schematic diagram you've drawn.
Okay, this is the D term, perfectly tuned.
That's probably...
And now I think we're ready to plug in the antenna. So I will plug that into pins 3 here.
6 assists, about almost 4,000 more than Jason Kidd ranked 4,000.
Let me adjust the frequency.
Is required. This is referred to as the canonical form. When it, over 1,000, I'm pulling it up now. The blue drop is at 9. And we'll lack support because number 1. Hello, those communicating they need. And their husbands are clueless. 56 might be the best known number in sports.
Homemade op amp, which we built up stage by stage in the...
The blue LEDs point up and the red LEDs point down. Use an accelerometer to get a picture.
Gently roll.
One thing I want you to remember as we go through these labs is it's not just about building the circuits, it's about understanding what you're doing. The real goal of your building these circuits is for you to gain through practice an understanding of a bunch of electronic concepts that we'll cover from beginning to end of the course. By the very end of the course, we'll do some pretty sophisticated stuff, like you'll see how the inside of a computer works in principle. Along the way, you'll build your own amplifier, you'll build a radio receiver, you'll build a little circuit that sends an audio signal through infrared light from one side of the room to the other. You'll build a little circuit that uses feedback control, pretending that it's controlling the vertical motion of an elevator. So the idea along the way is really to remember through repeated use some key ideas in our study of electronics. So it's not just about rushing through to get things built. It's really about taking the time to understand what we're doing, how it works, why we're doing it. So try to bear that in mind. So here's part 1 on page 3. We call it beeping out the breadboard. So here on the lab handout is a photograph of a digital multimeter, and here's a photograph of a breadboard. Here is the actual digital multimeter in my hand, and here is the powered breadboard that we'll find convenient throughout the semester. So the main component of this box, this powered breadboard box that you can see here, is this white section called a breadboard. You can actually remove the breadboard part of this powered breadboard, and so I can hold it up like this. So that's what we're going to do for today. We'll work with this, just this piece flat on the table. The chassis can sort of conveniently angle this, which is sometimes convenient for working without hunching over your work. But for today, we'll just work with it flat on the table. You're welcome to do that if you like, or not to, whichever you prefer in the lab. This thing is called a digital multimeter because, well, its mechanism is digital, as in digital computer, and it can measure volts, voltage, it can measure resistance, ohms, it can measure electric current, amps. So this will become one of our most valuable tools throughout the semester. It probably helps for you to go through a copy of lab01.pdf. I won't go through all the text as I work, but you should read through the text. Our first task is to figure out which holes on this breadboard are internally connected to one another. And to do that, we're going to use, well, we could use the ohms measuring feature of the digital multimeter, but the ohms measuring feature actually has an audio feature that will beep if the resistance is small. But we're going to use that beep feature because it will give us immediate audio feedback about whether things are connected or not. The multimeter has 2 leads. By convention, the black lead goes to some reference voltage, which we normally call ground. It doesn't have to be ground with the multimeter, but when you measure voltages, for example, you measure a voltage difference. What is the red voltage with respect to the black voltage? So it's red minus black. So usually the black terminal is called common or reference or ground, and then the red terminal is the point of interest you're probing. In our case, we really are looking at a symmetric situation. We're just looking at the resistance between 2 points. Notice that the digital multimeter has places where you can plug in cables. So we're going to plug in these so-called banana lead cables, a red one into this input that says volts and ohms and a couple of other features, and then the black one where it says COM for common. There's a different set of receptacles where you plug in the cables for measuring current. We're not measuring current right now, we're measuring resistance. If you're measuring resistance or voltage, you use the right-hand side here. So there's a little volt symbol, it has a little omega for ohms, and we will turn this, well, I could turn it to ohms, but if I turn it to ohms and then I push the yellow button, that's like second function on your calculator, that's beep mode, and if I touch the 2 leads to each other, it will beep. Okay, this is inconvenient for probing the breadboard. So I'm going to take a little piece of black wire, and I'll make it maybe 5 to 10 centimeters worth of black wire, and I'll take a little piece of red wire, you know, maybe 5 or 10 centimeters worth of red wire, and then I will strip a few millimeters of insulation off the end of each one. If you strip too little insulation, then the wire doesn't go all the way into the breadboard and doesn't make a solid contact. If you strip too much insulation, then there's so much bare wire sticking out that you can accidentally make inadvertent connections because neighboring pieces of wire will just run into each other, right? The whole purpose of the insulation is to avoid making unwanted connections. So if the stripped part is too long, then then too much of the wire protrudes out of the breadboard and it can accidentally connect with things in some adjacent column where you didn't think you were making a connection. So you'll kind of get used to stripping maybe a third of a fingernail width of wire off, of insulation off the end of the wire. I'll connect the black lead to the black clip, and I'll connect the red lead to the red clip, and then if I touch the red end of the wire together with the black end of the wire, it beeps. Now, what is connected to what here? We could be completely empirical about it, but I'm just going to flip this whole thing over. And you notice that there is a pattern of lines. So there are vertical lines that look like this and like this, but they only go sort of halfway across. And then there are horizontal lines that go across, but they again only go halfway across. So anyway, this seems like a big hint. It seems as if there are a small number of long horizontal connections, strips of metal, and then there's a large number of short vertical connections. So now let's see if we can make some reasonable hypothesis from that piece of evidence. So it seems as if everything in this column is connected to everything else in this column. So if I connect this right below, it starts beeping, and I can do anything in that little column, and that is connected. That works. But if I go over by a column, it's not connected. So it appears that things in the same column are connected, things in different columns are not connected. And then there's one more little observation we can make. If I go to the same column but above this little rib through the middle, it's also not connected. So this little column of 5 holes is separate from every other column of 5 holes. It's also separate from this column of 5 holes directly beneath it. We will see later in the course that these regions where you have 2 columns separated by one of these sort of rib areas are very useful for DIP, so-called dual inline package DIP chips. So then you have a row of pins on the top and a row of pins on the bottom, and then you can connect to all of these bottom pins and all of these top pins without shorting them to each other. That's why the columns come in pairs. So you can plug an integrated circuit chip like this in and wire it up. But we'll do that later. Another thing to notice is it appears that everything in this row is connected to everything else in that same row. These are the little horizontal rows on the top, and that's not connected to this other horizontal row on the top. Now, another tricky thing to notice is that, okay, these are in the same row. Now, you might expect that as I continue to the left, I'm still in the same row, I'm still in the same row. What happens when I go to the left-hand side of the breadboard? You would think I'm still in the same row there, but in fact, on most, but not all, breadboards, there's a divider in the middle, so that this top row on the right side is separate from this top row on the left side. That actually is a really frequent source of confusion when you wire things up, and so on most breadboards you'll see that previous semester students have put little jumper wires across this gap in the middle, so that if I connect the top row here to the top row here, it beeps. But the reason it beeps is the presence of this little jumper wire, little bridge wire. So you probably want to install those little bridge wires and leave them in place for the rest of the semester. Don't forget to check that they're there. Let me reinstall those little bridge wires. Okay, there we are. So the pattern we're seeing is that these things are all connected to each other, these things are all connected to each other, these things are all connected to each other, these things are connected to each other, these things are connected to each other, these things are connected to each other, and so on. So each of these little 5-segment columns is connected within itself. That's also true of these little 5-segment columns down here, but they are not connected to the 5-segment columns directly above them. So these 5 points are connected to each other, but they are not connected to this, and they are not connected to this. And then at the vertical extremes, there's a different pattern. These are all connected to each other. 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 You know, these are all connected to each other. 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 And then it's very convenient to make a connection like this with a little bridge wire. And to make a connection like this with a little bridge wire. So that once you've done that, now this entire row is interconnected, and this entire row is interconnected within itself. That will turn out to be useful when we use a power supply voltage, and let's say we want to distribute 15 volts. Let's say we want this to be plus 15 volts, and then every point along this row will be plus 15 volts, and maybe this will be 0 volts, which we also call ground, and maybe make every point along this row be ground. Okay, so you may see us do that either toward the end of this lab or in the next lab. Now, if you notice, when the multimeter is in the ohms position, if we have no connection, so the resistance between these 2 points is infinite or some gigantic number, this says 0.L, which is its way of saying overload, or it's really its way of saying infinity, or a bigger number that I'm able to measure. And then if I touch these 2 wires to each other, okay, so I see with the 2 wires in the same column of the breadboard a reading of about 1.3 ohms. And I think I can do that with my finger, 1.2 ohms. So you see, when there's a good solid connection, you'll get a number on the order of an ohm. It's often a fraction of an ohm. And then when there's no connection, like if I move these to completely unrelated columns, then you see OL, overload. So you should see in a drawer labeled Today's Lab Components, 3 LEDs, red, green, and blue, and 5 resistors. And the resistors' values you don't know, so we're going to try to figure them out. And we will measure them, and we'll also look at the stripes. Let's start with the first one. You won't know what order to pick them up in. So I'll take just the ordinary clips from the digital multimeter in ohms mode. We're still in ohms mode, and I read 199.4 ohms. So we read 199.4 ohms. If you look closely, there are 4 narrow stripes, and then there's a little bit of a gap, and then there's a wider stripe. And that wider stripe after the gap is always brown on our resistors because we have 1% resistors, and brown means 1. So that 1 is for 1%. Every once in a while, you might see a resistor, then instead of 4 stripes and then 1 separate one, there are 3 stripes and then 1 separate one, and then that separate one will usually be gold meaning 5%. But in our classroom, nearly all of our resistors are 1% resistors, which means this big stripe all by itself is brown for 1%, and then there are 4 other stripes. So in this case, red, black, black, black. So red is 2, black is 0. So it's 2000, which means 200 times 10 to the 0 power, which is 200 ohms, which is compatible with our measured value of 199.4 ohms. These are 1% resistors, so we expect agreement to within 1%. This color code, you don't have to memorize it, but it's occasionally useful just for double checking. Normally you want to measure the values of the components you pick out of the drawer, but just to see whether you're wasting your time picking up the wrong component, it sometimes helps to remember. Black, brown, and the colors of the rainbow, red, orange, yellow, green, blue, violet, indigo is skipped, and then gray, white. Black, brown, Roy G, Biv, gray, white. It's pretty easy for me to remember black, brown, ROYG, and then I have to kind of count on my fingers after that. Okay, I'll pick up our next resistor. And I measure 495.8 ohms. So the pattern of stripes I observe here is yellow, white, white, black, and then the usual brown one for 1% tolerance. And we measured 495.8 ohms. So yellow 4, white is 9, black is 0. 4990. So that's 499 times 10 to the 0 ohms. This black one is the exponent. 4990. And that's 499 ohms, which is certainly within 1% of 495.8. So we wanted something that was nominally 500 ohms, but it turns out when you're buying 1% components, they don't have to make 500 ohms, they can make 499 ohms. And that's of course within 1% of your desired value of 500. So the nominal values aren't always round numbers. Our next resistor measures 0.988 kilo ohms. So 988 ohms, 0.988 kilo ohms. So the pattern of stripes I see is brown, black, black, brown, and then the offset brown stripe. So that's brown, black, black, brown. That's 1001. That's 100 times 10 to the 1 ohms, which is 1,000 ohms or 1 kilo ohm. So that's pretty much 1%. It's actually off by just a tiny bit more than 1%, I guess. It's off by something like 1.1 or 1.2%. That's sort of unusual. Okay, the next resistor, 1.990 kilo ohms. And the pattern of stripes we see is red, black, black, brown, and then the brown 1% stripe. So that's 2001, or 200 times 10 to the 1 ohms, which is 2,000 ohms or 2 kilo ohms, which is certainly within 1% of 1.99 OK. It's 0.5% off. Then for the last resistor, we read 9.93 kilo ohms, and the pattern of colors we see is brown, black, black, red, and then the brown 1% stripe. So that's 1002, or 100 times 10 to the 2 ohms, which is 10,000 ohms or 10 kilo ohms. That makes sense for 9.93 kilo ohms measured. That's within 1%. Okay, let's move on to something more interesting. So let's start part 3 on page 7. So we'll take our ordinary alkaline battery, and we'll use the digital multimeter to measure the battery voltage. So we'll put the digital multimeter into DC volts mode, and we'll take the red clip and the black clip. So if we connect this in a normal way, red to red, black to black, so in other words, red goes to the positive terminal of the battery, which for a 9-volt battery turns out to be the small one, and black goes to the negative terminal of the battery, which for a 9-volt battery turns out to be the big one. Then we should see a positive voltage. Okay, so we measure 9.23 volts. So we want to put the battery, a 200 ohm resistor, and a red LED in series. So here's the battery, here's a 200 ohm resistor, here's a red LED. This is nominally 9 volts, but let's just call it VBAT since it might be slightly different from 9 volts. So an LED is an example of a diode. Current will only flow in one direction through a diode. So the way I have it drawn here, current can flow from top to bottom. Anode, the current goes in. The cathode, the current goes out. Current will not flow up through this diode. So we need to make this terminal more positive than this terminal to get current to flow through the LED. And in fact, it needs to be more positive by an amount that corresponds roughly to the energy of a red photon in electron volts, which turns out to be a little under 2 volts. Okay, let's build the circuit on the breadboard. First, we need to figure out which of these resistors is actually the 200 ohm resistor. So it should be red, black, 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 200 times 10 to the 0. So the stripes sometimes help you to narrow it down, and then you want to measure it with the digital multimeter. Okay, that's a resistance of about 200.2 ohms. So now we want to wire up the circuit. I'll put the battery somewhere on the left. I'm going to use the black wire for a designated ground. So I'm going to use this bottom row here to be ground. You'll see that that turns out to be useful later on. I'm going to use this upper row to be my plus 9 volts. That doesn't matter in this circuit, but you'll see that as we build other more complicated circuits later, we will often distribute a voltage to several different places. Here's my 200 ohm resistor, which I will run from plus 9 volts down to some little column here. And maybe I'll even try to orient the resistor so that It sort of looks like the schematic where the resistor is running horizontally. And then I'll take my red LED, and the convention for diodes and for LEDs in particular is that the lead that is longer is the one that should be more positive when current flows. So if you look carefully, you can see that the lead on the right side is a little bit longer. It's maybe a millimeter or two longer. So that should correspond to the top of the triangle. This is the positive side of the LED if it's going to be illuminated. So I'll put that in the same column as the end of the resistor that's not going into the battery. And then I'll go down to this row that I designated ground. Oh, look at that. So you get this very satisfying result when you've wired up the circuit correctly, that the LED lights up. So it's sort of immediate feedback that you've done something right. So I'm going to label the points on this circuit A, B, C, and this is the same as point C. This is also point C. And then let's see if Kirchhoff's voltage rule works out. So VAC, we think should be 9.23 volts. Let's see if that's still true. So one way to do that is simply to clip on to the lead of the resistor that is connected to the battery. That's point A. And then we can clip the black lead to the lead of the LED that's connected to the other end of the battery. So that's node C, and that should be a measurement of VAC. Okay, so that should be VAC. Well, we see about 8.93 volts. Aha, and I think what that's telling us is that the battery voltage is a little bit lower when there's actually a current flowing than when there's a negligible current flowing. So this is something we'll talk about in a moment. I also switched to meters because the meter I was using before seemed not to give very steady values, so I'm trying to debug that in parallel with recording this. Now, it's sometimes nice to be able to plug in directly to the nodes on the breadboard. So for that, I'll take a little piece of red wire and connect it to the red lead on the meter. And then I can plug right into this plus 9 volt row on the top of the breadboard. And I'll take a little piece of black wire and put it into the black lead on the voltmeter. And I'll plug that into this lower. And I see 8.89 volts. Now, one thing I'm curious about, I'm going to remove the resistor so that the current is now negligible. Okay, I see more like 8.99, 9.00 volts. It's interesting that we're not quite back to 9.23 volts. Okay, we're at 9.07 volts. Now let's reconnect the circuit. So I'll remake the connection at point B between the resistor and the LED. Okay, number one, we get the very satisfying result that the LED lights up. Number two, we notice that the battery voltage drops a little bit to 8.94 volts. We're foreshadowing a little bit the fact that a real-life voltage source tends to supply a bit less voltage as the current that you draw from it increases. Let's say this is 8.90 volts when there's actually a load connected. And then we can measure VAB. So VAB, I mean VA minus VB. So I'll put the red wire on point A, the black wire on point B. So here's the red wire is already on point A. So I'll move the black wire for the meter over to point B, which is this column, and I see 6.70 volts. And then we can measure VBC, which is basically VB minus VC. So to do that, I'll unplug both wires of the DMM. I'll put the red wire between the resistor and the LED, and I'll put the black wire at our circuit ground, which is the bottom point of the LED. And I see 2.19 volts. And Kirchhoff's voltage rule says that VAC minus VAB minus VBC equals 0. So you go up at the battery and then down across the resistor and down across the LED. Going around the circle, you should get 0. Sure enough, I think if we take 8.90 minus 6.70, what's left is 2.20. You subtract 2.19, and within 0.01 volts, this works. So we can infer the current. Since this circuit has only one branch, there's only one current. That current goes through the resistor to the right, it goes down through the LED, it goes back up through the battery. So we can say that this 6.70 volts equals IR, and that gives us the inferred current is 6.70 volts divided by 200.2 ohms, which is 0.0335 amps or 33.5 milliamps. Okay, now let's use the same meter. We could have used the other meter, either one of these digital multimeters, to measure the current flowing through our circuit. To measure the current flowing through a circuit, you have to interrupt the circuit. I need to break the circuit. Let's just suppose we break it here. And then we'll stick the ammeter here between these 2 points. So if this point was B, then I don't know, we can call this point B prime maybe. So these are now 2 different points on the circuit. Although for an ideal ammeter, the voltage drop should be 0 across the ammeter. In real life, there'll be some small resistance of the ammeter, but an ideal ammeter should have a negligible resistance, because you want an ammeter ideally to perturb the current that it's measuring as little as possible. So we'll have the red wire of the ammeter at point B and the black wire of the ammeter at point B prime, and that should be a positive current running through the ammeter. So just remember this, an ammeter always has to be in series with the circuit that you're measuring. You can't put an ammeter in parallel with something. You also have to be a little bit mindful that you don't inadvertently run a very large current through an ammeter, or you can blow the fuse on the ammeter, which then kills 10 minutes of your life changing the fuse. So we will leave the black wire in this common input to the multimeter, and I'll put the red wire into the microamps milliamps connection, and then I'll move this over to the milliamps setting. Oh, and then I just did what I told you not to do. I left the current meter in parallel. That's really bad. Okay, so now I'll move the bottom end of this resistor at the top end of the LED over to a different point on the circuit. So now this will be B and this will be B prime. So I'll stick the red lead of the current meter at B, and then I'll stick the black lead of the current meter at B prime. And we see about 33 milliamps. That's pretty good, 32.7 milliamps. Okay, so we measure 32.7 milliamps. Now you might ask, why do we measure a current that's a couple percent lower than we inferred from the resistor value? And it turns out there actually is a resistance of this digital multimeter when it's measuring ohms. I didn't just now look up the actual value, but it's typically on the order of a few ohms. So I think if instead of a 200 ohm resistance we had 200 plus a few ohms, I think that would be enough to explain this difference. Yeah, so if the series resistance of this ammeter is 5 ohms, then that would explain the difference. So just as a little experiment, I just took this ammeter and I put it in ohms mode, and I used it to measure the resistance of this ammeter when it's in milliamps mode, and I got about 3.6 ohms. So this one, it doesn't have a nice round number, but anyway, that's about the right scale to explain our little less than 33 milliamps instead of a little more than 33 milliamps. Let's go back and try the same thing with the first digital multimeter. So to put it into current measuring mode, I'll leave this in the common plug, and I will move the red wire over to the milliamps receptacle, and then I'll turn this to milliamps mode, and I'll plug the black end into the point we're calling B prime, and I'll plug the red end into the point we're calling B. Okay, and satisfyingly we see the circuit is completed by the presence of the multimeter. The LED lights up, and we see 31.2 milliamps. This is the 37XR-A DMM. This other measurement was the DM6000 DMM. So we actually know from the data sheet, from the specifications, that the internal resistance of this meter when measuring milliamps is 10 ohms. So instead of 200.2 ohms, we have 210.2 ohms. So then we would expect 31.9 milliamps. Okay, we got 31.2. And to really get to the bottom of that, we could go back to measuring volts. We might see that the battery voltage has dropped a tiny bit from using the battery for several minutes. You can make these measurements more precisely when we use a real laboratory benchtop power supply instead of a battery. So that should allow us to get things closer to the 1% level. So I could go back to volts mode on this multimeter, and I can remake this connection, and then we can measure VAC. We get 8.69 volts. Okay, so you see, I think the battery has worn out a little bit while we've been using it. 8.68 volts. And then VAB, so here's point A, we can move this over to point B. VAB is 6.50 volts, and then VBC, 2.17 volts. And then the inferred current with 200.2 ohms is VAB divided by 200.2. There's 32.5 milliamps. Then we can go measure the current directly with this thing in current measuring mode with the DMM in current measuring mode. So I will put it in milliamps mode, and I'll move this over to the milliamps receptacle, and then I'll break the connection between the resistor and the LED, and I'll put the red lead by the resistor and the black lead by the LED. Okay, we have 30.90 milliamps, and if we plug in 210.2 ohms, then we expect 30.92. There we go. Okay, so we actually predict 30.92, we measure 30.90 milliamps. So when we do the measurement quickly enough that the state of the battery doesn't really change, the chemistry of the battery hasn't had time to wear out a little bit. So it's a little bit tricky working with batteries, because you have to complete the measurements on a time scale much shorter than the time scale for the electrochemistry of the battery to degrade through the steady flow of current. So let's go back to measuring voltage with the digital multimeter. So I will rejoin points B and B prime on the circuit, so now they're the same point, and then I will measure the voltage between point B, which is the same as B prime now, and C, and I have to move this over to volts, and then I move this to the volts setting, and I see 2.18 volts. So I have VBC equals 2.18 volts. This is for the red LED. Okay, so this point is now just point B. Now, what happens if we put a green LED in place of the red LED? Well, the energy of a green photon is larger than the energy of a red photon, so we think that's going to correspond to a larger voltage drop across the LED to produce a green photon. Let's see. I see 2.47 volts, and then let's replace the green LED with a blue LED. A blue photon has higher energy than a green photon. I see 2.93 volts for blue LED. And you say, what is a typical wavelength for a red photon? It's something like 630 nanometers. And then how about a green photon? It's something like 540 nanometers. And a blue photon, I think something like 470 nanometers. And then the energy is E times V. Charge electron times voltage should be Planck's constant times C over lambda. H nu, or HF, is the same as HC over lambda. And this isn't exact, but you should have a little more than that. Voltage across the LED should be something like Planck's constant times the speed of light divided by the charge on positron photon divided by the wavelength of light. So if you just plug in numbers, I get 1.97 volts, and then I get 2.30 volts, and I get 2.64 volts, which certainly shows the right trend. It's not exact because the voltage drop across the LED is going to be higher than that needed to produce a red or a green or a blue photon by some amount. Okay, the next thing we're going to do is we're going to use a switchable resistance here. We're going to swap out resistors so that by using smaller and smaller resistors, we'll be drawing a larger and larger current from the battery. So our circuit will basically have just a battery and a resistor. We also have a current meter to measure the current flowing through the circuit. There's only one branch in the circuit. And then we'll also have a voltmeter to measure the voltage across the battery. So we'll do that over here. So we'll use two meters, one to measure the voltage across the battery and one to measure the current through the circuit. And one thing we will observe is that the more current we draw from the battery, the lower the battery voltage becomes. And the simplest model we can make of that is to fit for a linear relationship between the current drawn from the battery and the voltage supplied by the battery. And it turns out that a linear relationship between that voltage and that current is equivalent to there being a little internal series resistance. So a real-life battery behaves like an ideal battery in series with a tiny little internal resistance. Don't confuse that with the external resistor, whose purpose is to set the current that we draw from the battery. This little internal series resistance of the battery's internal resistance, later we'll use the word Thevenin resistance. This is a parameter of a model that lets us say that as you draw more current from the battery, if you draw no current, then let's say the battery's voltage is the full 9 volts. And then as you draw more and more current from the battery voltage will drop more and more below 9 volts. So you'll get a smaller and smaller voltage from the battery as you try to draw more and more current from it. That may be familiar from trying to start your car when the headlights are already on. You notice that when you turn the key to start the engine, the headlights dim because the additional current drawn by the starter motor causes the voltage supplied by the battery to drop below the nominal 12 volts of your car battery. So we need two digital multimeters. We will use this one, the Amprobe 37XR, to measure currents. The reason we do that is we have a good number from the datasheet for this DMM for the internal resistance when it's measuring current, the internal resistance of the meter. The meter also has an internal resistance. So we'll see that things that aren't supposed to have resistors in them behave as if they have resistors, or in some cases they actually do have resistors. So we'll see that a real-life battery is like an ideal battery with a little resistance in series that we call the internal resistance. And a real-life current meter is like an ideal current meter with a little resistor in series. And then we'll also see later that a real-life voltage meter is like an ideal voltage meter with a very big resistance in parallel rather than in series. It's in parallel. So we'll use this meter to measure current. We'll use this meter to measure voltage. In the lab, you won't use this alkaline battery. You will use a super heavy-duty battery, and that makes your measurements easier. This alkaline battery has a very small internal resistance. It's small enough that it's not very easy to measure. It's not a very obvious effect. So in the lab, for this part of the lab, you'll use a super heavy-duty battery, which has a much higher internal resistance. And the reason we do that is it gives you an effect which is easy for you to measure. I happen not to have a super heavy-duty battery with me, so I'm going to use the same alkaline battery. So I'll get a smaller internal resistance than you will get in the lab. So I'm going to put this in current measuring mode. So we'll put this on the milliamp scale, and this is plugged into the milliamp receptacle. We'll put this one on the DC volts scale. Oops, and this is in the volts setting. And then I will plug the black wire from the battery down here, and I'll plug the red wire from the battery up here, and then I will measure the voltage across the battery. Put the red terminal from the voltmeter in the same row as the battery's positive terminal, and I'll put the black terminal from the voltmeter in this same bottom row where the black terminal of the battery, the negative terminal of the battery is, and I get 8.83 volts, and that's when we're drawing 0 milliamps. There's no current flowing except the tiny little bit of current that flows through the voltmeter. So we will see later in the next lab that the internal resistance of a typical voltmeter is about 10 mega ohms. So this is actually a really tiny current, like a microamp, flowing right now when all that's connected is the voltmeter. Now we want to connect a 10 kilo ohm resistor, and then in series with that we'll connect the ammeter. So the 10 kilo ohm resistor should be brown, black, black, red. 100 times 10 to the 2, brown, black, black, red. I happen to have a third multimeter off to the side, so I will just double check that this is a 10k ohm resistor. I just want to make sure I have the right resistor. Its exact value doesn't matter for this exercise. I just want to have the right one in my hand. This is 9.99k, so this is the correct resistor. So I'll put one end of the resistor in this red. See, here's the red battery terminal, here's the red voltmeter terminal. So I'll put one end of the resistor up there. So that's basically like giving out the battery voltage to everything that wants it. And then I'll go into this little column, and then we'll just use the ammeter to complete the circuit from here down to the place where all the black terminals are going. So here's the red terminal of my ammeter. So I'll connect that to the bottom end of the resistor, and then I'll take the black lead of my ammeter and connect it where the black lead of the battery and the black lead of the voltmeter are already connected, this little row down at the bottom. So I see 8.83 volts from the battery, and I see 0.88 milliamps flowing through the circuit. And that's about right, because if you have about 10 kilo ohms and a little less than 10 volts, then you expect a little less than a milliamp. Okay, and you'll see a more dramatic effect. See, this V battery should change by something noticeable in real life in the lab with your heavy duty battery. Now let's go to 2K, which should be red, black, black, brown. I'll check with the external ohm meter that this is the resistor I'm looking for. So this third meter is on ohms mode. I see 1.998 kilo ohms. And so I'll pull out this 10K resistor and replace it with this 2K resistor. Okay, we see 8.82 volts. Again, you'll see something more dramatic in the lab. And 4.4 milliamps. And again, order of magnitude, that makes sense, because if you had about 10 volts divided by about 2K, you get about 5 milliamps. Okay, the next we want 1 kilo ohm, which should be brown, black, black, brown. Okay, with the external ohm meter, I measure 0.995 kilo ohms. So I will pull out this 2K resistor and put the 1K resistor in its place. And I see 8.80 volts, and I see 8.7 milliamps. And again, you will see a much more dramatic effect in the lab. Now let's go to 500 ohms. I think it's actually 499, so that's like, it's yellow, white, white, black, 499 ohms. I'll just check it, 496 ohms. Pull out this 1K resistor, I'll replace it with the 500 ohm resistor. I see 17.2 milliamps and 8.75 volts. Now this has been kind of unimpressive so far, so let me add a data point that you won't do in the lab. Because the internal resistance of this alkaline battery is so low, I have to draw quite a bit of current from it to see a significant voltage drop. Let me just do that. I will plug in place of this 500 ohm resistor, I will plug in a 100 ohm resistor, brown, black, black, black. I'll go from this row where the positive terminal of the battery and the positive terminal of the voltmeter are connected to this little column where the positive side of the ohm meter is connected. And I see 77.2, let's say 77 milliamps and 8.53 volts. Then we pull that out. It's actually warm to the touch, so I'm dissipating a significant enough amount of power in this little 100 ohm resistor. When I picked it up, it actually was noticeably hot to my fingers. So you want to be careful. These resistors are rated for 1/4 of a watt. That's related to how much surface area they have and how quickly the ambient air can conduct away thermal energy. So if you run a large enough current through one of these resistors to dissipate more than 1/4 of a watt, then it actually becomes hot enough potentially to burn your fingers. So watch out for that. So here's our 51 ohm resistor. I will put that here. And I see 141 milliamps and 8.3 volts. Okay, take that out. Ouch, it really is quite hot. Ooh, ow, ooh, ow, ow. Okay, it gets hot. Okay, I used Python to make a graph, and the result was, then here's the current in amps, and here's the battery voltage, volts. We have about 9 volts here, 8.83 volts, and then we have a slope like this, and the slope that came out of our fit was minus 3.8 ohms. Okay, so if you have a graph of volts versus amps, then the slope of that graph is measured in ohms, and this is a downward slope, so it's a negative slope, but this corresponds to as if the battery had a little 4 ohm resistor in series with it. Then you would get that linear relationship between the measured battery voltage and the current that you draw from the battery. And here is my graph made in Python. So it's not a bad fit for a straight line. This 4 ohm internal resistance of the battery is small enough that it's kind of a hassle to measure. That's why in the real lab you will use a heavy duty battery that has more like a 30 or 40 ohm internal resistance instead of this 4 ohm internal resistance. It's just more obvious, an easier effect to measure. And there's my Python code. For this last part, part 5, we are going to replace the battery with a benchtop laboratory power supply. So this large device is basically as close as you'll ever come to a perfect voltage source. It supplies a voltage which, to the best of its ability, is independent of the current that you draw up to a limit. In this case, the limit is about 3 amps. So we'll turn this device on, which basically turns its brains on and makes it ready to start thinking about supplying voltages, but we still have to tell it what voltage to supply. So what we want to wire up here is the benchtop power supply and a 200 ohm series resistor whose purpose is to limit the current through the LED so that we don't burn out the LED. And then here's a red LED, and then we have the ammeter measuring the current through the resistor, which is approximately the same as the current through the LED because the current drawn by the voltmeter will be negligible. And then here's a voltmeter measuring the voltage across the LED. So then we're going to attempt to measure the current versus voltage curve for the LED. So the voltmeter measures the voltage across the LED, current meter measures the current through the LED, and the assumption is that the current through the voltmeter is negligible compared with the current through the LED. So that this current meter is telling us, in essence, the current through the LED. And this benchtop power supply, unlike the battery, will supply a voltage that, as long as we stay within its rating of supplying a current less than 3 amps, its output voltage will be exactly what we ask for. So we'll get the battery out of the way, and in place of the battery, we will use these 2 wires. On this particular power supply, we have a red wire on the positive terminal and a black wire on the negative terminal. The supply at your station may use different color wire, but anyway, bear in mind there's the one with the plus sign and the one with the minus sign, and I'm going to connect the one with the minus sign, the black terminal, to this lower row on the breadboard. And in fact, while I'm here, I'm going to swap things around so that the little jumper wire is black on this side that I traditionally use for ground. Okay, the black wire is going to this lower row on the breadboard, and the red wire, via our positive voltage, is going to this upper row on the breadboard. So this is a good habit we want to form. So we'll use this row up. Here's our working area. We'll use this row for our positive voltage, and we'll use this row for the return, which we usually call ground, but the return to the negative side of the power supply. Then let's use this meter to measure current. So it's already set up to measure current. So I'll put the red wire from the current meter to the red wire from the power supply, and that should give us a positive number for current flowing out of the positive terminal of the power supply. And then I will run the black wire from the current meter into some unused column. Then we'll take the 200 ohm resistor, which we expect to be red, black, 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 and I confirm that with the third digital multimeter that is off camera. So I get 199 ohms. So I'll put that resistor, one end of it will go where the black side of the current meter is connected, and the other side will go to some new unused column on the breadboard. Then we'll take the red LED. So the longer lead is the side that wants to be more positive for the LED to conduct electricity, to light up. So that longer end will go into the same column where we just put the second side of the resistor, and the shorter end might as well go into this bottom row of the breadboard that we're using for ground, for return to the negative side of the power supply. Then we want to connect the other multimeter, this one, which we'll use to measure voltage, and it's already set up to measure voltage. The red cable is plugged into its volts or ohms input. So I'll put the black end of that voltmeter to the bottom row of the breadboard that I'm using for my ground connections. So this is like here, this point B, here's point A. So point B on the circuit is this horizontal row of the breadboard, and point A of the circuit is this horizontal row of the breadboard up top. Okay, now the red wire of the voltmeter will go where the resistor meets the LED. Maybe I'll call that point C. So the red side of the voltmeter is at point C in the circuit. Then we can put the current meter in milliamps mode, and we can put the voltmeter in volts mode, and let's try 1 volt. So I'm going to push the 1 button. See, if I push the 2 button, that's channel 2, and the 3 button is channel 3. We're using just channel 1 for now. And then I'm going to say 1 volt, and then I'll say on. And this indicator lights up to say this channel is on, channel 1 is on. Here's the positive side, here's the return. And then it says 1 volt, and it reads back 0.00 amps, so it's either nothing or a small fraction of an amp. Then our voltmeter reads 1.00 volts, and our ammeter reads nothing. Let's try 2 volts. Well, we can write this down. Here's the power supply voltage, here's the LED voltage, and here's the current. And this was 1.0 volt, and this was 1.0 volt, and this seemed to be 0. Let's try 2 volts. 2 volts. So this is 2.0 volts. So the LED voltage now is 1.70 volts, and the current is 1.44 milliamps. Let's try 3 volts. We have 3.0 volts programmed. The voltage across the LED is 1.804. Let's call that 1.80. 1.80 volts, and 5.69 milliamps. Let's try 4 volts. So we programmed 4.0 volts. We get 1.878. Let's call that 1.88. 1.88 volts across the LED, and we get 10.1 milliamps flowing through the resistor, presumably flowing through the LED because the resistance of the voltmeter is 10 mega ohms. So a really tiny current will flow through the voltmeter, negligibly small for our purposes right now. Let's try 5 volts. So we programmed 5.0 volts. We get 1.94 across the LED and 14.5 milliamps current. Let's try 6 volts. By the way, notice now that the current reading on the power supply is 0.02 amps, which makes sense. Something like 20 milliamps, but with just one significant figure of precision. So we see 2.00 volts across the LED and 19.0 milliamps current through the LED. Let's try 7 volts. That's not a very big change. That's 2.06 volts. So we could instead use the dial feature. So if we you can move, it's a little hard to see, you'll see it better in the lab, it's hard to see on the camera, but I can change which digit I adjust by turning the knob. And so if I change it, now I'm moving 1/10 of a volt at a time, and then I can look at the voltmeter, and it might make sense to choose equal steps in voltage, or it might make sense to choose equal steps in current. Let's say what gets us 30 milliamps. I'm going to dial up the voltage till I get, okay, this is about 30 milliamps. So I have 8.5 volts programmed and 2.145. Let's call that 2.14. 2.14 volts across the LED, 30.2 milliamps through the LED. Let's go to 40 milliamps. So I'm just going to dial this up 1/10 of a volt at a time until I see 40 milliamps on the current meter. I'll go slowly. Okay, so I'm at 10.7 volts on the power supply and 2.27 volts across the LED and 40.0 milliamps through the LED. We could go for 50 milliamps. I think we want to stop pretty soon, but we can go for 50 milliamps. Turn the knob until I see about 50 milliamps on the current meter. There we go. Okay, so I'm at 13.0 volts on the power supply, 2.40 volts across the LED, and 50.3 milliamps current through the LED. So now let's make a graph. You don't need to spend any time making a real graph. You can just draw some data points by hand and put a curve by hand through your points, but I have a computer here. I'll use Python to make a graph. Okay, I typed in my voltage data points and my current data points, and I made a graph, and you can see that the current is pretty negligible until we get to about 1.6 or 1.7 volts, corresponding roughly to the energy of a red photon. And then we see this sort of rapidly rising curve. For a regular diode, not an LED, you would see an exponentially rising curve, but for an LED... Okay, that's my illustration of the basic lab techniques I hope for you to pick up during the first lab.